to the next talk. It will be a remote talk to be presented by Hemal Shah from Broadcom. He's a distinguished engineer and system software standards architect in the Data Center Solutions Group, DCSG division at Broadcom. He leads and manages a team of architects. He has been in this community for many years. Before joining Broadcom, Hemal worked at the Intel Corporation, where he led the development of system silicons, many projects, and he actually now serves as the Senior VP of Technology in the DMTF and project co-lead in the OCP hardware management projects. Hemal, if you are ready, please feel free to share your slides, and if you can turn on your video, yes, we can watch you. Yeah.
Yeah, can you guys hear me?
Yeah.
Okay.
The slides are not being shown. Just
yeah, I'm going to share.
Okay.
Hello, everyone. Unfortunately, I won't be able to see others, but hopefully you can see me and my voice is coming okay. Let me share my slides.
You should be able to see actually all of us in one screen. I don't know.
I can, but then I won't be able to see.
Yeah, I know. I'm just telling.
So
we are not invisible people, okay?
Right. No, I can feel the energy in the room.
Yeah. Okay.
Okay. Thanks, everyone. Thanks for inviting me for this talk. Just a quick background on before I get into the talk, and I know we are a little bit running late here, so I'll try to see if we can catch up. So in last couple of years, as we have been actively participating in MWAP user group, these meetings, and we have introduced our Thor family of NIC, which supports the Rdma technology. And we introduced that. We also went over all the features that we have in there. In this talk, what I'm going to focus on, as this technology has already matured, I want to focus on what software support that we have, as well as what's our philosophy behind Rdma software support. And I'll focus on HPC, AI machine learning market specifically. First, I'll introduce the components, and then we'll focus on Linux baseline, and then what we have for the HPC market, as well as peer memory direct. So that's roughly the outline. So to recap, this shows the Broadcom Ethernet NIC that we introduced last year. There are 4 key tenets of this. At the core of that, as you can see, is the RoCE for the Rdma functionality. From the Ethernet side, this is where all the connectivity, port configuration, we have device which is built on low latency data path, and the pipeline that is designed for the device has very high packet per second performance. From the RoCE standpoint, there are some key offloads. Of course, the whole transport and RoCE functionality, including the interface from the verse bin below. In addition to that, you need some other functions from the deployment standpoint, which includes the quality of service. This is where both the network level as well as the host level QoS functionality that is part of the device. Also, for virtualized environment, we have seen that there are things where you want to track things on per flow basis, whether it's just statistic, or you want to apply on per flow basis NCAP and DCAP kind of functions in the hardware. So those are some of the flow processing offloads that can be combined with Rdma. And then from just the virtualization, hypervisor bypass, SRIV, and also there is this technology which came before SRIV partitioning. What this means is you have a single port which can be partitioned into multiple physical functions, and each one can have its own QoS, and you can independently enable RoCE functionality on each of that partition. So those are some of the key core offloads that you need for RoCE. and also Rocky to work with the QoS and virtualization infrastructure. Then the third tenant here, as you look into any deployment of RDMA, as you start looking into scale, congestion control becomes very important. And yesterday in our benchmarking talk, we talked about the importance of congestion control and then ability to have the network utilization very high during the congestion, react to congestion faster, ability to control the rates of QP. For all that, you need the hardware support. So for the whole congestion state management, the QP level rate control, a group of QPs that you can control targeting as destination, their rate. Additionally, as you see the switch infrastructure for Ethernet, that's congestion control scheme is all based on the ECN marking. So in addition to those switch infrastructure, having the endpoint have the ability to mark the ECN as well as when it receives the ECN, generates the CNP in the hardware. So those are some of the key components that allow you to have congestion control hardware support, which enables at scale deployment. And then the fourth tenant here is the software support, which is going to be mostly the focus of this talk. In the last couple of years, we were focused on the other aspects which I just mentioned. So the way we look at the software piece is you have the underlying, the baseline, which is where the verbs and UCX support comes into picture. And then you start moving up in the layer. I'll talk about the MPI layer, how Broadcom Ethernet NICs are supported, what MPI support is already available. And then recently we have seen accelerated devices as well as GPUs and others coming into picture where they are running these workloads and having direct access to their memory. So a NIC or performance NIC having ability to directly transfer data in and out of those peer memory is very important. And then along with that, there is increasing focus on the collectives. All these different devices have their own collectives communication library, which may directly interface into higher level collective operation, or they may be used independently by applications. So from the NIC standpoint, you also have to support those infrastructure. So I'll get into those also. So this is really what are key tenets of Broadcom Ethernet NIC. Today, I'll focus on the software piece. So first, let me quickly summarize. We do support all different operating environment, Linux, VMware, Windows. For Linux, primarily, this is where the key components, those are open source upstream user mode library that is part of RDMA core, the kernel mode driver that is also all upstream, also included in distros, so being inbox. We also have this peer memory module, which is out of box, and then I'll get into some more details on that. This basically enables the peer memory data transfer. So those are all the data path related software component. In addition, you need tools which allow you to have the policy configuration, number of NVM configuration that you need for the deployment. And in order to have those configuration being automated and scripted, we do provide a set of installation configuration script, which basically simplifies your Rocky configuration deployment. There are also standard Linux tools, eTool, DevLink, LLDP tool that people use for various control plane management plane functions for Rocky. Those are all supported. We provide the underneath support that comes from driver, and then it fits into this infrastructure. So pretty comprehensive Linux software support. VMware, this is where the ESXi has its own infrastructure support. which includes where we have our kernel mode driver. We also have support for PV-RDMA, and this is already enabled by VMware. They have their own CLI tools through which you have QoS and DCP configuration. This is ESX CLI. We support that, as well as our standard NVM configuration tools are also applicable in that environment. And as you can imagine, for Windows, similar user mode kernel library kernel mode driver. There are 3 different RDMA modes you can think about here: RDMA or physical function, their own version of para-virtualized RDMA or VNIC, as well as when you enable SRIV RDMA or VM. So those are all supported mode. And then same thing there about the NVM configuration, as well as supporting the standard tools that Windows has. And for all of this, we have in the device for the control plane, the RDMA resource management, we have hardware abstraction layer, what we call hardware resource manager, which is being exposed to all of this host-based software component. This abstraction layer is OS independent, allows us to have driver being independent from the underlying hardware details. Also, it gives us the resource isolation as well as virtualization. And also, there is a security aspect of everything being managed by the secure firmware, which is always securely booted and securely updated. The control plane functionality is considered secure. And that's also a key component here that comes along with all this other software component I talked about. I have a link in here, which is a public link where you can get some more information about our software support that comes with the Ethernet link that are deployed. So this is really a quick summary of all the software components. For the rest of the talk, I'll focus on the Linux, specifically for this community, also on HPC applications. So Linux, we zoom into the Linux RDMA core project. If you look at it, Linux RDMA core project has been around for quite some time. It's mature. All the library support for connection management, address management, upper level IB verb support is already in there. So these are already part of, all these components are part of major Linux distro and kernels. Broadcom component which fits into this is our user space library, which is shown here in yellow, libnxdre. We continue to upstream that as we add more features, enhance it. We also have out-of-box version of that, because generally there is some time between when you introduce the feature and when it gets accepted upstream. Similar thing for our kernel mode driver, which is part of the Linux kernel. It's upstream in the Linux kernel tree, bnxdre. We have also a companion driver, which fits into the auxiliary driver model, which is for our non-RoCE traffic. So this basically builds your core Linux RDMA software. And as you can see, we fit into standard infrastructure. Our philosophy is to have everything upstream open source. So building on top of this shows you a little bit into how things are layered. So when you talk about Broadcom Linux RoCE components, as I mentioned, the user mode library, the kernel mode driver. Also, we have our NIC driver, which takes care of all the non-RoCE traffic, TCP/IP stack. It is also a companion driver to the RoCE driver, which allows basically the common policy for resource management around things like the MSIX vectors, the completion queues, and so on and so forth. So they both are coupled that way. And the control plane firmware, this is where both drivers are using the abstraction layer to get to the resource management services. There are some advanced software features which are split between the user mode, Rocky user mode library and kernel mode driver. And these are targeted for scale, deployment. There are things which you may have heard about because different workloads will need different profile. I mean, sometimes what you optimize for low latency path may not be also the same configuration that you will use for high bandwidth. So this is where we have introduced this performance profile concept through which you will have a default one which is more balanced, but you can also select one which is optimized for specific aspects of application. And we continue to enhance this kind of advanced functionality. Other one here that is listed is when you talk about multiple processes at scale, from user mode, submitting requests, getting completions, updating completion, arming for completions, all those results in generation of doorbell traffic, which goes over PCIe. For various reasons, that can create congestion in the device as well as on PCIe. So for the robustness of driver, what we have in the user mode library as well as kernel mode driver, ability to pace the rate at which the doorbells are being submitted to the hardware. Also, when if there is a congestion being detected by the hardware, then the doorbell, if there is a congestion and if doorbells are dropped, they can be recovered by the software. So these are like key features which really enable your deployment, because as we see more and more cores being available, we start seeing the processes per node continue to go from what used to be 64 to now 128 to 256, and it's going to be higher. So that it's very important. The way these features are designed in software, they have minimal impact on your data path when there is no doorbell congestion. So there are a lot of software design and architecture work that goes into how those features are implemented in this. And those are purely software features, and that's why I want to highlight. In addition to what you support in your data path, these are some of the companion features that are really needed. And the last one here, there's some more, but I'll mention is error recovery. Ideally, everything works nice and well, then there's no issue. But when there's some error detected by the hardware or firmware, we have the capability to trigger a recovery from the device, and then the user mode library as well as drivers will participate in that without really impacting the application. And then that will result in basically restoring the resources. So this is also important, though this may happen rarely or never. You need to have this kind of functions being part of your software infrastructure. So that's really the core software that's in Linux. Now I'll get into the HPC AI machine learning. What you see in here is as you move from left hand to right hand, you are moving up higher in the software stack. So the first one, as I mentioned, that's your core. It is aligned with Linux kernel. Modules are upstream. User library is part of the Linux Rdma project. The other important framework here, which we have seen widely used, is UCX, which is richer in terms of providing higher level programming model where applications or libraries can use things like collectives, higher level messaging semantics. And the way it's structured or architected is you have the high level APIs to which the libraries, upper layer libraries and application will interface. And then you have the lower level transport. And this is where our verbs provider fits into. And this is how the UCX can be supported. And it doesn't require any application level modification. They can just use the UCX semantics and underneath take advantage of Broadcom Rdma networks. And then similar thing here for MPI. the picture here shows MUG'22, but there are similar layering in MPI libraries where you have the top level APIs which applications are using, and then underneath you have the transport layer, and how you interface to that, it comes through the lower level verbs provider. So MPI can run directly over verbs. We have seen also MPI can run over UCX, and then underneath UCX can use verbs. So we do support multiple MPI implementations, including OpenMPI, MUG'22, as well as Intel MPI. And the philosophy here is basically plug into the provider framework, support either direct verbs path as well as the path MPI is going over UCX. And this is where there are aspects of those layers where there are accelerated functionality, which the provider, when it supports, results in better latency, better throughput. So those are all the software tuning efforts, software infrastructure support really requires. So that's our existing infrastructure support for HPC, AI, and machine learning application. Recently, we have seen there is a new class of application, as I was mentioning. I'll coin a term here, peer device, but what these peer devices are, they are basically offloading some of the compute aspects from the CPU to whether this is a GPU or some other accelerator, which is optimized for HPC machine learning application, or TPU. You can name any of those. From the RDMA NIC standpoint, the support infrastructure is very simple. In order to expose the peer memory, RDMA, basically we want to transfer data directly in and out of those memory. And this is where using peer memory module, you interface with those peer device driver, so that this is how you will have ability to register the memory and have the right set of translation for you to have direct access from the NIC. As RDMA operations are performed, you can directly transfer data in and out of that memory. This may require also interfacing with their user mode libraries also. So that's the model where today where the industry is. There are proprietary module being used. There are a couple of them. We have our own peer memory module which can interface with the GPUs, as well as NVIDIA has its NVPeer memory module, which allows you to interface with NVIDIA GPUs. Going forward, those two are already supported. There are already applications that are using those. They work with Broadcom Ethernet NICs, which are Thor family NIC. Going forward, what we have seen, Linux has this DMA buff infrastructure. That is generic infrastructure, which is basically allowing using standard software infrastructure to import, export memory from a peer device to the RDMA NIC. And that is what we are planning to add support. With that support, we should be able to interface with any accelerator device which has the other side of support for DMA above. So this is, in our opinion, open source generic infrastructure which will enable a new set of application and accelerator without requiring NIC to have per accelerator specific support for either their libraries or drivers. So that's one area for peer memory direct support. Other one, what we have seen is with all these accelerated devices, the vendors of those, they are putting forward their own libraries, which are optimized for between the device as well as on the network kind of collective communication. As we know, for HPC and machine learning applications, the collectives are very important, depending on which application you are talking about, but whether it's all reduce, all to all, scatter together. So all these vendors, they have their own optimized collective communication library, including the MPI libraries. So all these collective operations, underneath, they are using verbs. There is significant amount of work that is needed in tuning those collectives. And we work very closely with those collective libraries to make sure underneath the Broadcom Ethernet NIC capabilities and the verbs path is optimized for collective performance. And that is very important. Also, while doing that, we want to make sure that doesn't require any kind of application level modification, because those applications sitting on top of that, they are primarily interfacing to those collective libraries. So this is our two key areas where how we support the peer memory direct access as well as collectives. So in summary, I provided a quick overview of all the baseline software component for Broadcom Ethernet NICs, which are widely deployed in various markets, specifically the markets that are of interest to this conference workshop is HPC and machine learning. Our philosophy has been making sure that the ease of use, deployment, and configuration for somebody to deploy this RDMA software, we continue to focus on that. As the software matures, which is, as I mentioned, I talked about all the standard infrastructure that we support. We basically continue to focus on enhancing that support, either via software features, some of the advanced features I mentioned, as well as adding support for more infrastructure, as well as tuning for specific infrastructure that are in use. And with that, I'm going to take a pause here. If you have time, I can take some questions. I know we started a little bit late.
Thanks a lot, Hemal. Let's give him thanks. Any questions? We can have time for one more question. No? Okay, so thanks, Hemal. Giving a very broad overview of the approach you are taking, and so people will be following up.
Right. Thanks,
okay.
Everyone.
Yeah, thank you. So let's move quickly to the other talk. Jitin,